Hey guys, I hope you're all doing good. In this video, you are going to be learning how to set up a shock tube problem in CONVERGE. Now, shock tubes are important devices. They have a lot of applications. Primarily, they are used to basically study chemical kinetics. Now, the idea here is you can actually see a shock tube in front of you. There are two regions. There's a left-hand side region and a right-hand side region, and there's a diaphragm. Now, the diaphragm is basically separating the two regions. You might ask why you need that. Well, the answer to that question is on one side you have high pressure zone and then the other side you have a low pressure zone. So what happens is this diaphragm is actually broken, and when the diaphragm gets broken, the interface is no longer there, and because of that the fluid in the high pressure zone is going to enter the low pressure zone, and depending upon the pressure difference, shock waves can develop, and the shock waves can reflect from the walls, and you can get refraction waves. So you can get compression and expansion waves in this process. And in real life, what people do is they fill the chamber with fuel and air, and because of these shock waves, right, what's going to happen is there is going to be auto ignition. Because of the pressure waves, the fuel and air are going to auto ignite because typically temperature is also higher. And what you can actually determine from the shock tube data is how long it takes for the fuel and air to combust, which is what you call as ignition delay. And typically this is how ignition delay data is obtained for chemical kinetics calculations. And hence shock tubes are extremely important, and learning how to simulate it is also going to be very useful, because what you can actually do is you can set up the experiment and you can test out a reaction mechanism, and you can see if the simulation prediction for ignition delay matches with your experimental data. All right, so let me actually play this video. Now, before I do that, let me explain what you're going to be looking at. The top image and bottom image represent the same geometry at the same instant of time. Now, the only difference is that the top geometry shows species concentration. We are actually showing you the concentration of nitrogen. So the way the case is set up is that on one side you have nitrogen and the other side you have oxygen. Okay, and here you are seeing velocity. Initially the velocity is actually zero because the diaphragm is intact, and hence there is no flow. So when I actually play the video, you can see that the diaphragm breaks. You can see that the waves are getting reflected back and forth, and in the process mini shock waves are also getting developed. You can see that this right here is your diamond shock wave pattern. Now on the top, things take place a bit more slowly. Okay, so I'm just going to play the video from start again. The species concentration actually goes up, but it gets pushed back because of the reflected wave. Now when the shock front hits the wall and comes back, it's actually preventing the mixing process. Do you see that? That's what's happening here, and it's causing that little recirculation zone, and it keeps on occurring. Now if this was a reacting flow problem, meaning if you had air and fuel, then you can also simulate the combustion process here, right? Overall, it's a very exciting and interesting problem to set up. Now the main reason why I'm introducing you this problem is to give you an introduction to shock tube, and also explain another important concept called as regions. Now when we set up the conjugate heat transfer problem, we learned how to set up two regions, the fluid and solid region. Now in this case we are going to be setting up two regions, and one shortcut trick that you need to learn is, or actually a checkbox called as group color by regions. If I click on that, you can see that each of the triangles are getting colored by a region, right? So this is one region and this is another region. So what I have here is, if I just bring it up here, you can see that I have two regions. I have a high pressure region, which is colored in green, and low pressure region, which is colored in brown. Okay, so these are my two regions. So how did I set it up? Well, it's fairly straightforward. When I flag the boundaries, I flag it in such a way that, I have a high pressure boundary, which is this guy. Maybe I can just hide it all and then show it one by one. So this is my high pressure boundary. All right. And since this is a 2D simulation, I have my two 2D boundaries, and this entire thing is going to define your high pressure region, right? With all these faces, you can define a volume, and which is what CONVERGE requires to create that into a region. Right? So for example, here with all these faces, I can construct a volume. I hope you can see that. And that is what is happening here. So CONVERGE is using all these faces, and since we have assigned regions for it, it knows that this is a separate region. So similarly, if I uncheck this guy, hide all, and then show you the low pressure region, the boundary flagging is very similar. So we have a low pressure boundary, and then we have two 2D boundaries. Okay, and then when you connect it, you have your entire case setup. All right, so this is going to be more of a blind simulation test for you, meaning I'm not going to be showing you how I set it up from scratch. I'm just going to be giving you some pointers. This is more like a project for you. You're going to be figuring out how the boundary flagging needs to be done, and then how you need to assign the regions. What I'm going to be talking about is two things. In the initial conditions, I have two regions. I have a high pressure region, which has a 6 bar pressure and 300 Kelvin temperature, and a low pressure region where it's atmospheric. Now, one thing that I'm doing is I'm creating something called as events. What is that? So whenever you have two regions, with the help of events, you can actually either connect them or disconnect them. What does that mean? So in this case, we have two regions, right? We initially don't want the flow to take place from the high pressure region to the low pressure region. All right. But after some time, we can actually enable the flow, right? Which is very similar to popping the diaphragm in experiments, because in a simulation, you cannot pop a diaphragm, right? It's not possible. So we actually do that by creating these events. So let me show you what this is. This is fairly simple. So when I click on this, I have 4 tabs. Click on the sequential tab. You can see that there is a start time, 0 seconds. So at 0 seconds, the high pressure region and low pressure region are closed, meaning they're disconnected, no flow can take place. But then at 0.001 second, which is 1 millisecond, the two regions are open, after which they completely stay open. And that is why you see that the shock is completely propagating. Okay, so this is one thing that I want to mention. The other thing is I'm setting this up as a transient simulation, and I'm running it for 0.003 seconds. Okay, so 3 milliseconds. So let me close this. The final thing that I wanted to talk to you about is adaptive mesh refinement. Now in adaptive mesh refinement, I'm basically doing a species-based AMR, and you can just copy the settings that I have here. I'm using nitrogen as my AMR species. Type is permanent, and then the SGS embed level is 0.001. We still haven't talked about adaptive mesh refinement. We haven't discussed the theory, so I'm not going to be explaining this. For now, just use this number and try to set up the simulation successfully. Okay. As far as creating the animation, well, you can actually use this setting. You can see that you need to get the 3D output data at 1e minus 5 seconds in order to get a smooth looking video. And the time interval for text output can be 1e minus 6. Note that there is no inflow or outflow boundary here. It's completely walls. So that is why after some time, once you get an equilibrium condition, the pressure will reach a steady value. You can actually check that out by monitoring the data. Okay, so with that, I would like to conclude this video. Like I said, this is going to be a blind test. I think I've shown you the required information to set up the problem. I do have the raw geometry file. It's provided to you as well. Use that to set up the case. And if you have any questions, let me know. All right. Thank you. Bye.